Let's talk about standing waves in this lecture. Before doing that, let's understand few things here. We have been writing that the equation of the wave is y equals a sine omega t plus phi. Now, well, this is the same as equation of a simple harmonic motion. When we said the wave actually traveled like this, something like this, and is the amplitude y that is changing with time. But we said that the difference between the simple harmonic motion and the wave motion is that this wave is also traveling forward with a velocity v, when we know v equals lambda t, lambda over t. Let's observe one thing. Let's say here at some time t, the whole thing is, let's say, something like phi prime, and the wave repeats itself after a time period t, or you can also say a wavelength lambda, is the same thing. Then here it's phi prime, but here it's going to be phi prime plus 2 pi. Why? Because you see, this whole thing is increasing as the time is increasing. So here it's phi prime, so it's sine phi prime here. But after one time period, this whole thing becomes omega t plus phi prime, where you see this is the time taken from here to here, and this is nothing but 2 pi plus phi prime. So what you get is sine 2 pi plus phi prime. Now see, these are the same value, have the same value, because that is true. We know that sine phi prime is same as sine 2 pi plus phi prime. But the problem is that the angle keeps on increasing, the angle inside the bracket, which usually we do not do in physics. So to make sure that we do not repeat the angle, which means you can say that the angle goes from 0 to 2 pi, and then 2 pi to 4 pi, and then 4 pi to 6 pi, we expect the angle to go from 0 to 2 pi, and then from 0 to 2 pi, and then from 0 to 2 pi. Okay, and we can do that, and that's one thing. And the other thing is that wave is traveling forward in the, let's say, positive x direction, and this also needs to be incorporated, and this can be done by writing y equals a kx minus omega t plus phi. So instead of writing wave like this, we write the wave equation like this. It doesn't make any difference. Why? Because let's say this is the wave equation, and let's see how the wave equation looks after time t and lambda and wave and distance lambda. Okay, so let's say the initial whole thing, as we said, is phi prime, so it's actually y equals a kx minus omega t plus as a matter of fact, we want to say this. We want to say kx prime minus omega t prime plus phi equals phi prime. So here it's x prime comma t prime. Here it's phi prime plus 2 pi, and x prime plus lambda, and t prime plus t. So phi has gone from phi prime to phi prime plus 2 pi. Distance has gone from x prime to x prime plus lambda, because there is one lambda, and t prime has gone from t prime to t prime plus capital T. Okay, so this is the initial condition. Then the condition here can be written as y equals a k. Now x is actually x prime plus lambda minus omega t prime plus t plus phi, and you can see that this is nothing but k prime x prime plus k lambda minus omega t prime plus, well, in fact, minus omega t plus phi. And this is nothing but a sine, I forgot a sine here, I should have written a sine, a sine phi prime, because k lambda equals omega t, so they cancel each other, and we are left with just this thing. So we started with a sine phi, here it was actually y equals a sine, again forgot sine here, a sine phi prime, and we ended with a sine phi prime, and when the two are separated by a lambda and separated by a time period. So this is the proper way of writing the wave equation, kx minus omega t. Also, this equation tells the wave is traveling in the x direction. As we can see, omega is changing, as kx is changing positive in the positive direction. So the way to write equation is y equals a sine kx minus omega t plus phi. If the wave is traveling in the negative x direction, then you can rewrite the wave equation as a sine kx plus omega t plus phi. Well, it should have been more understandable if we had just put minus x here to make it minus kx minus omega t. So instead of putting plus, well, or let's discuss this. So this is x in the positive. If you want to go in the x in the negative, what you'll expect is to write something like this. So x becomes negative now. But this whole thing can be rewritten just because the way sine behaves as a sine minus kx minus omega plus kx plus omega t plus phi. Now this phi is different from this phi. These two phi's are different. If you want, you can put a 1 on 2. But this is a general equation. We are talking about general equation. This is the general equation of any wave traveling in the negative x direction. And this is the general equation of any wave traveling in the positive x direction. Okay, so by writing the equation like this, we have overcome two shortcomings. First, angle will not be more than 2 pi. Second, this tells that this is moving in the x direction. And this tells that the wave is moving in the negative x direction. Okay, with this understanding, let's talk about standing waves. So, what is a standing wave? Let's say you have a wave traveling in the forward direction, and you have a wave which is traveling in the backward direction. We already have seen this animation, and we know that, let's say if this wave is y equals a, and let's call this the positive x direction. So this is a sine kx minus omega t, and this guy is y equals a sine kx plus omega t. Now when these two waves meet, if you can refer back to the animation, when these two waves meet, they will produce an interference pattern, something like this. And you can simply add them to get sine kx and times cosine. You get 2 here. It will be actually 2a sine kx and sine cosine actually omega t. Now what is special about this? You see that this equation is not showing equation of a traveling wave. This wave is standing at one point. You see x is not for some certain x, the wave is breathing is changing the amplitude with time. So you see, like if you fix x, then y for any fixed x is 2a sine kx cos of omega t. So y is changing with time. Y is changing with time y is changing with time, only with time and not with distance x. And only with distance, it's not changing with distance but only with time t. Okay, which means sort of breathing up and down. So you see it's breathing up and down, that's it, for any x. Okay, but there are a few more things. You can see that for k equals 0, y is 0. For k equals, we know that k is the wave number and defined as 2 pi divided by lambda. So for k equals lambda over 2, y is again 0. And for k equals 3, no, I should have actually, sorry, not k equals 0, well actually for x equals 0, y is 0. For x equals lambda over 2, y is 0 again, and x equals 3 lambda over 2, y is 0 again, and so on. So 5 over lambda 2, 6 lambda over 2, and 7 lambda, and so on. And these are called the nodes of the standing wave. Similarly, you can see for x equals lambda x equals lambda over 4, you see that y is 2a cos omega t, and x equals 3 lambda over 4, y is 2a cos omega t, and so on. So here this value is 0 for all these x's, and this value is a maximum, or 1 or 2a actually, for these kind of values. You see that here kx is, here you say kx is 0, here kx is pi, and kx is 2 pi. So for all these values, sine is 0. But similarly, sine is maximum, or 1 or minus 1, for all these different values. Okay, so and these are called antinodes of the standing wave. And these are called the nodes of the standing wave. So for example, your standing wave may look like this, or your standing wave can look like this, or you can add more lobes. So these are the nodes, and this is the antinode. Okay, and we'll solve some problems on standing waves to really understand what's going on.